Hello, my name is Cyril Alain-Racoterson, and I'm going to present our work on distribution-based invariant deep network for learning metafeatures. This is a joint work with Gwendoline Deby, Gabriel Perret, and Michel Sebag. This work addresses the AutoML problem, which, given a search space of machine learning data, the goal is to find the optimal pipeline for a given dataset. Two approaches to tackle this AutoML problem are the hyperparameter optimization approach, aiming to improve existing black box optimization, or the meta-learning, which has the goal to learn from a set of tasks. In this paper, we propose an approach to tackle the meta-learning problem with an application to tabular dataset. The approach on meta-learning is dependent to the format of data. For tabular dataset, one cannot reuse model trained from previous tasks. Instead, what we can do is to look at transferring surrogate model, compute meta-knowledge from an offline benchmark, or find the most similar task, then pick the best performing machine learning pipeline on this task, and finally solve the new task with this pipeline. Finding this similarity between datasets is the reason why we need metafeatures. It refers to a vector of descriptors of the dataset, and the point is that similarity of datasets are defined as the distance of their metafeatures. However, to our best knowledge, the state-of-the-art metafeatures to describe tabular datasets are dominated by manually designed metafeatures. They include shallow metafeatures, statistical metafeatures, and landmarking. Our intuition is that even if these handmade metafeatures have been shown to improve AutoML systems, they are still very limited. For example, two datasets can be similar with respect to their handcrafted metafeatures, but very different with respect to the AutoML problem. To overcome this issue, we propose to learn dataset metafeatures. Two main challenges for learning metafeatures are, first, the produced metafeatures should be invariant to the dataset features, and sample permutation. This is because permuting the samples should not affect the representation of the dataset, especially for tabular dataset. The second challenge is to define the learning task to train these metafeatures. Our contribution is a neural network architecture that satisfies the invariance properties of the metafeatures. The name of our approach is DIDA, referring to distribution-based invariant deep architecture. DIDA proceeds by capturing the interaction between two samples with respect to its feature and target values. The invariance is then obtained by averaging over the learned representation. Interestingly, learning from pairwise interaction of feature and sample allows our approach to have nice theoretical properties. As experimental validation, we compare DIDA with other invariant neural network architecture. As a benchmark, we consider patches of dataset which are obtained by randomly subsampling the initial dataset. And finally, two meta-learning tasks are considered. The first is patch identification. The goal is to classify whether two patches are from the same dataset or not. The inputs are two patches and the output is a binary target. The results we have on this task show that DIDA is competitive to the best baseline dataset to VEC. The second learning task considered is to run configuration. This task is to predict if the performance of one configuration is higher than the performance of another configuration. The results we have on this task show that the proposed DIDA approach behaves better than the baselines. To summarize, we propose a novel neural architecture called DIDA to learn dataset metafeatures. The experimental validation shows the merits of this proposed approach on two proof-of-concept tasks. Do not hesitate to reach out for more information about the work. Thank you very much.